All right, so if you're in the pharmaceutical sciences, you know we're surrounded by chemicals every single day, from drug discovery all the way to manufacturing. But how do we actually manage the risks that come with them? It's not just about ticking boxes on a safety checklist, right? It's really about mastering the science of safety itself. So let's dive in and break down what that really means. We see these symbols plastered all over the lab. They're so common that, honestly, it's easy to just tune them out, but we can't. Recognizing what these mean and really respecting them, that is step one. It's the absolute foundation for keeping yourself safe, your team safe, and making sure your work has integrity. You can think of it as the universal language of lab safety.
Okay, so here's our game plan for today. We're going to start with the basics. What even is a chemical hazard? Then we'll get into classifying risks, how exposure happens, and the all-important hierarchy of control. And we'll wrap it all up with some key takeaways specifically for your careers in pharma. All right, Section 1, Understanding Chemical Hazards. First things first, we got to build our foundation here. Because if we're not precise with our words, how can we possibly be precise with our safety procedures?
So, what's the official line? It's actually pretty straightforward. A chemical hazard is any substance with the potential to cause harm. And I want you to really focus on that word, potential. It's the key. A chemical can be sitting there, totally inert in a bottle, but that potential for harm, it's always there, just waiting for the wrong set of circumstances.
And that leads us to a really important but kind of subtle distinction. What's the difference between a hazard and a hazardous chemical? Well, think of it like this. The chemical hazard is the idea, the abstract potential for harm. But the hazardous chemical, that's the actual stuff in the beaker, the solid, the liquid, the gas. Getting this right helps us separate the inherent property of a chemical from how we actually manage it day to day.
Okay, moving on to Section 2, classifying chemical risks. So we know what a hazard is. Now let's start sorting them out, because not all risks are created equal, right? We basically break them down into two big buckets. Physicochemical hazards, the ones that mess with property and physical safety, and then health hazards, which, well, they mess with us directly.
First up, physical chemical hazards. These are all about raw energy and reactivity. You know these guys. We're talking about things like ethanol, super common solvent, but also super flammable, or sulfuric acid, which is incredibly corrosive. These are the chemicals that can literally cause fires, explosions, or just eat through stuff on contact. They're the immediate, kind of threat in the lab.
Now, on the other hand, you've got health hazards. And these are personal. They hurt us. Sometimes it's immediate, but other times the damage builds up over years. We're talking about carcinogens like benzene, or toxins that target specific organs. And check this out. Naproxen is on the list as a nephrotoxin, something that harms the kidneys. It's a fantastic reminder that even the drugs we create to help people can be serious hazards for us in a concentrated lab or manufacturing setting. All right, Section 3, Exposure and Impact. So, we've got these chemicals, we know they're hazardous, but how do they actually do any damage? It all comes down to one thing, exposure. How does it get from the bottle into your body, and what happens once it's there? Basically, there are four main ways in. You can inhale it, breathe in vapors or dust. It can get on your skin. You could accidentally ingest it, swallow it, or you could get injected, like from a needle stick. And out of all of those, inhalation is often the scariest for systemic effects, because once it's in your lungs, it goes straight into your bloodstream and zips around your whole body, fast. So what determines how bad the damage is? Well, it's not just one thing. It's a whole mix of factors. You've got to consider what the chemical is, of course, but also what's its concentration? How long and how often were you exposed? And what state is it in? A solid, liquid, or gas? Just think, something as simple as heating a liquid can create a ton of vapor, and suddenly the risk of inhaling it skyrockets. Okay, let's jump into Section 4, the hierarchy of control. Look, knowing the risks is one thing. That's half the battle. But the other half is actually controlling them. And when it comes to safety, there's a gold standard for how to think about this. It's not just a random list of things to try, it's a hierarchy, ranked from the most effective strategy all the way down to the least.
So here's how it works. At the very top, the best possible solution are engineering controls. Think fume hoods or special ventilation systems. Things that physically remove the hazard from your space. A step down from that, you have administrative controls.
This is about changing how people work, like rotating jobs or limiting work hours in a certain area. And then, at the very bottom, as the last line of defense, you have PPE, personal protective equipment. Your gloves, your goggles, your lab coat. Why is it last? Because it depends entirely on you doing everything perfectly. A fume hood is always on, always working. But gloves, they only work if you pick the right ones, put them on correctly, and never ever mess up.
All right, last section, let's pull all of this together and talk about what this means for you, specifically in your pharmaceutical career.
And this right here is really the bottom line. How you manage chemical hazards isn't just some annoying safety rule. It is fundamental. It directly impacts the quality of your research, the integrity of your data, and ultimately the safety and effectiveness of the drugs you help create. It's not separate from the science. It is good science.
Okay, so if you're going to remember anything from this, let it be these points. First, know the difference between a hazard, the potential, and the chemical, the actual stuff. Second, be able to classify if it's a physical-chemical risk or a health risk. Third, always remember that risk isn't simple. It's a mix of concentration, duration, and how it gets into your body. Fourth, the hierarchy of control is your best friend. Engineering first, then administrative, and PPE is always last. And finally, number 5, and this is a big one for us in pharma, the very medicines we make can be hazards in the workplace. Never forget that.
So, I'll leave you with a question to take back to your own lab. The next time you're in there, just look around. Are you guys relying too much on PPE for something that could be fixed with a better engineering control? Could a process be isolated to make it safer for everyone? Really thinking critically about safety isn't just another task on your to-do list. It's a mindset. And honestly, it's a mindset that's going to define your entire career as a great, responsible scientist.